All right, so the ugly cobalt, like this is legit the title of this video on the premium channel. I think I talked about it, but I didn't show it to you. Just want to show you the search feature. So if I want to find that video, just type in ugly, right? There it is. That's the video that I'm going to show you guys. The ugly cobalt, not your typical evap and pressure sensor faults. That is the one that we're going to be covering right now, okay? So the ugly cobalt, I guess I had that in the slides. Probably should have reviewed my slides before I showed you that. There it is. There's my search. Type in ugly. There's the ugly cobalt. So let's get our perspective here. That is the guy that I'm messing with. It's an evap vent solenoid. Pretty typical controlled component. It's a 2-wire device, and I'm doing some voltage measurements just real quick on both wires. And this screen capture at the top, it is the lab scope in a graphing meter mode. I only picked that because, well, it's on video, I can show it easily, and then I can show the still frame capture on one. This is my yellow wire voltage right there. There's 2 volts right there, so I'm under 2 volts. And then this is my white wire voltage, again, under 2 volts. This is just me taking my T-pin out, trying to make contact, having bad contact, and then until I finally got it. So that's what you're looking at in that graph, okay? So what I'm seeing is roughly 1.57 volts on both wires, okay? Just key on, engine off. I'm not doing anything else, no bidirectional controls, I'm not commanding the driver on. I have a code for the evap vent, and that's what I'm looking at, those 2 guys right there. I pulled this up just to review with you guys power and ground side switching, because this circuit I'm saying is a ground side switch circuit. So I want to make sure that we're comfortable with normal circuit voltage readings on power and ground side switch circuits before we plug in this case study and variables and what you see. So power side switch we already covered. This is the guy that we talked about previously with the fuel pump circuit, right? Circuit off, my voltage here and here, let's do 2 measurements, would be what? Driver is off. What are we going to see on those 2 guys? Good, 0 and 0. Driver off on this device, this is a ground side switch circuit. Externally powered means it's internally grounded. This bottom one's ground side switch. What are we going to see with the circuit off here and here? 12. Very good, 12 here. If anyone was hesitant to say 12 on this one, I understand why. Because you have a source this way coming through a fuse on its way through a resistor. That's a resistor. And so we automatically look at that and say, well, there's going to be a voltage drop there. But remember your principles here, that with no current flow, you're not going to have a voltage drop. Okay? And so this driver is not connected to ground right now. It's closed off. So that pressure is going to come through this resistor. Doesn't matter what it is, right? 10 ohms, 100 ohms, 1,000 ohms. What if it's 1,000,000 ohms? There is a variable. And where's that drop coming from? My meter. Very good. So you see, we plug this in again. Meter can cause a drop if that resistance is too high, but in a sense, we could just say any resistor, any control, you're going to have 12 and 12. You're not going to have a voltage drop. No current flow equals no voltage drop. Everybody comfortable with that? 12 and 12. Normal circuit off voltage is 12 and 12. So I have this in my head. This picture's burned in my mind before I even go underneath the car and take these measurements. So let's go back to that. We have low voltage. Would you agree? It should be 12 and 12, and what I'm reading is 1.57 and 1.57. Questions so far? Everybody comfortable with that? What's some variables? What voltage levels should we be reading? We just said that. Should be 12 and 12. What could our problem be? There's a few here that we could talk about. At least 2 maybe that I'm thinking of. What's the first thing we should do before we ever attack a circuit problem like this? We have 2 readings. Are we sure that our meter is giving us the proper readings? That should be your next question. Every time you see something unexpected on a car, before you end up on a wild goose chase and start pulling diagrams and checking wiring and finding where your problem's at, you want to make sure, this is so simple, but it's so highly overlooked, you want to make sure that your meter has a good ground. Because if my meter has a bad ground, then these voltage numbers I'm getting here are skewed and I can't trust them. And so in the next capture, that's what I'm doing. I'm actually, in the video, I'm moving my ground because I'm in the back of the car. And what I like to do typically is wherever I'm taking a measurement, I'll put my ground for my meter. It's an alligator clip. The reason it needs to be an alligator clip is once you find that good ground, you never want to move it because we want to be able to trust it, because we're going to take our positive lead and move to different locations. And what we don't want in our troubleshooting procedure through that is we don't want to be saying to ourselves every time we take a measurement, is that ground good? Is that ground good? Is that ground good? Because that's the thought you should have in your mind, especially if you're using how many of you guys, when you troubleshoot, are using two pointed leads and you're holding one here and you're holding one here? If you do, Ed, you should get a ruler like the old nuns in the Catholic schools, and you should smack their hands every time you see them do that, because that is not troubleshooting. And every time you move that ground lead, you cannot trust the reading you have on your positive lead. You can't trust it. How do you know? How do you know? You don't know. You have to have a constant, connected, alligator clipped ground to a known good ground when you're troubleshooting. You will have so many problems if you don't adopt that procedure. So what I normally like to do before, especially if I see something unexpected, is I like to take my positive lead and hit something that I know does not have a problem, and use that as my guide to tell me if my ground is good. So maybe the plate light's back near me. I'll turn the parking lights on, and if it's an easy plate light to get to, I'll back probe the positive on the plate light and make sure I see 12 volts. Plate light's lit. I know that's working, and so if I don't see 12 volts, I know my meter's got an issue. So just keep that in mind moving forward, right? I'm moving this ground to different locations, and I'm just telling you that I didn't have the ability to check something known, because this also had a pressure sensor fault, and that was right here. I actually went over to the pressure sensor and did some measurements, and it was all messed up too, because there's faults on that circuit too. So I couldn't use that as my guide. And so I just moved to different locations. Just take my word for it. The ground is good. That's what I'm doing here. I'm moving the ground around, and then this is a steady signal, and I'm reading 1.66 volts. So originally I was 157. So did I improve my ground a little bit by seeing now 166? I did. And I think there's 169. Confirmed ground is good. Now what? So that's my question. My ground's good. That would be my one variable. Where are we going now? Both control and feed circuits show low voltage. So I'm reading, let's go to here. This is the picture you want burned in your mind when you're doing ground side switch circuits. Let's just call this 2 volts here and 2 volts there. Which direction would we go? Like towards the computer, maybe the solenoid, the driver, feed side of the circuit. Yeah, I'm not worried about the driver. Remember, driver's off right now. We're not really worried about this guy right now. This circuit is off. I'm going this way. Our problem is over here. What if the driver was like stuck on then? Good question. If my driver was stuck on, and this will be stuff that the more you see this, those numbers will be burned in your mind on what a normal circuit would be. So we said, I should have done this. It's my fault I didn't. 12 and 12 with the circuit off. What we're going to see with this circuit on, or even stuck on, is 12 on this side and 0 on this side. That would be what a stuck on solenoid would look like. If that driver was on all the time, that's what I would see, 12 and 0. So the 2 is never even an option for the driver being on all the time. And that's a standard piece you want to remember moving forward for any circuit like that. And when you throw computers in, it's difficult sometimes because we can't visualize those things, and it really involves, number one, the understanding in here. If you had a light bulb moment right now, that's good. You need that. But for that to stick, you need to see it out there on multiple cars, especially, and here's the ones that you really learn from are the ones that you make a bad call on. And then you're like, no, let me take that back. The ones you learn from are the ones you make a bad call on as long as you're not parts changing. If you change this part, that didn't work, then you change this part and that did work, but you're not sure why, and you didn't care, you're only worried about your bottom line flat rate number, and you want your income to be good, then you'll never get good at it. But if you take that scenario, regardless if you're dealer, whatever, even if the guys in the shop are making fun of you, why are you measuring that? Because I want to know, that's why. I want to know. So you make that bad call, you realize it wasn't the right call and why. You put the new part in, and when you're done, you spend 2 minutes taking voltage readings on the new part so you can burn that in your mind on why. You'll never make that bad call again, because it's like somebody took a hot freaking soldering iron and burned that in your brain. That's when it really sets in. So to encourage you guys a little bit, when you leave here, you'll never feel like you've learned enough. You won't. You just won't. Unless you're working in the field right now while you're here, that's really what will help you, but it's really the foundation here, and when you start seeing these problems, that's where you start learning this stuff. So 12-0 circuit is on. We're definitely on the feed side of the circuit, okay? We have a feed side problem to this solenoid. Well, let's go check the fuse. I pulled a diagram. You know, we could have spent time on diagram analysis and stuff like that. I'm not doing that here. I'm just telling you that this goes to a fuse. This circuit, I am looking for that fuse. I have 2 volts on this leg of the circuit, 2 volts here, 2 volts here. I'm not worried about the solenoid. I'm not worried about the control wire. I'm not worried about the driver, because if the control wire is open, what do we see? 12 and 12. If the control wire is shorted to ground, what do we see? 12 and 0. Same thing as if the driver was on all the time. So feed side for sure. I'm going after that fuse. Using my test light, 12 volts, test light's lit. It is not lit. That fuse is blown. So now we have another one of those WTF moments. Where is this voltage coming from? That fuse is blown. Where is this voltage coming from? That's kind of weird, man. Maybe. Could be. Short to ground, though, would do what with voltage? Think about this. Short to ground. Any wire, any component, any circuit, any car, any year. Short to ground. What is the ground on a car? What's the voltage level on a ground on a car? 0. If a wire is shorted to ground, what is your voltage going to be? 0. So it can't be a short to ground. Could be a short to some positive, some wire trace in between, you know, the 2 wires touching each other. Could be that. Could be that. Or could be, lesson for today, is bias voltage. This is messing me up too. When we saw Caleb, this is one of, you remember? You were with me. This is one of your first case studies filming with Dad. You were 16. This is like 4 years ago, and you worked with me on this. Yeah. I edited it, which is why you wouldn't remember like the editing part, but you were cameraman on this. In the beginning of this video, we have young Caleb holding the camera, not knowing this is what he was going to do for a living. Just pay attention, Caleb. Hold that camera here. I wish we would have kept some of that original footage. I just yelled at him all the time. It would have been nice to string together a clip of 4 years of me yelling at you. It could be internet gold. No, then I get people hating on me too. How you talk to your son like that? I didn't yell. I'm not a mean father. I'm just impatient sometimes. Sorry.
Lesson learned, right?
Yeah, it's kind of like we've all been there with dads. I had a stepfather, and he was like that. And I mean, I just did not want to hold the light for him, whatever he was doing, because I know I was holding that light in the wrong spot, and he was going to hit me. So, you know, that was my experience with Dad. So we've all kind of been there.
But working with you for the first 2 years is kind of like you're always holding the flashlight in the wrong spot.
Yeah, that is true. All right, fuse is blown. Fuse is blown. Why'd the fuse blow? We have multiple issues here. Well, multiple things we're thinking of now. Number one, where is this voltage coming from? I mentioned bias. It's going to be a bias. I'll show you how this ties in. Number two, would you guys agree with me? We have a short to ground somewhere we have to find. The answer with this car is not to just plug in a new fuse and give it back to the customer. We have a blown fuse. The case study addresses that. We go through some short to ground testing. This car was in an accident. This is about an hour and 20-minute video. Caleb and I were pulling our hair out trying to find this short to ground. We couldn't find it. And then we did some detective work. We looked at the fenders on the front of the car, and the lines were not right. Oh, that's right. I opened the door and it went clunk. And I'm like, that's not right. This car was in an accident, And then we did some further homework, and you see that this is inside of the, that's right inside the door. When you step in the door, that's the floorboard area. Somebody did some welding, and it went through the harness and shorted that wire right there to ground. That was how we found our short to ground. So it's great video to watch in locating shorts to ground that are intermittent, side note, but this is a bias voltage lesson. There's my short, that's why the fuse blew. This is after replacing the fuse. I'm doing the same measurements with it plugged in with a good fuse. I'm reading, I should have shown both, two pictures. I'm reading 12 volts here, and I'm reading 12 volts here. I know it says 1189, key's been on for a while, battery voltage is low. I see 12 and 12. Isn't that what we want to see on a ground side switch circuit? And so then I say to myself, well, okay, where was that voltage coming from? And I said to Caleb in the video, I'm like, oh, that's a bias voltage. And I proved it in this capture. I did the same measurement on the two wires, and I'm reading 2.92 volts with it unplugged. Unplugged. So you can't kind of see that here. This is plugged in, and this is unplugged, 292. And I'm sorry, unplugged, I only saw that on one wire. Caleb, I need to add some extra slides here, because I needed to emphasize that this picture, this is just the control wire that I'm on now. Okay, let's go back. Or no, we'll just go with my picture. Here's the explanation right here. I'm on the control wire for this component, okay? So I drew the picture for you guys. I added some extra stuff in here. Ignore this for a second. Just see if this looks familiar to you for what I drew previously. Externally, we have a fuse, right? That comes to a component. We'd have 12 volts here. We'd have 12 volts here. The driver is off. Okay? Turn the driver on. What's our voltage do? Drops to 0 on the control wire. Driver on. Normal circuit. No problem. But when you have this bias here, it's going to mess you up if you're not aware of it. And I did my best drawing my own simple dumbed down version of what this might look like inside the computer. It has a source. What is this source? Don't know, don't care. I don't know. It's 2.9. I don't know if it was 2.9 at the original or not, but here's the way this works. The computer has a sensing circuit. What you maybe are not aware of, the computer watches outputs. That's just your voltmeter. That's the computer's eyeball. So just picture this. The computer's watching that wire right there. It's watching it. Not relevant to the bias, just a side note. Okay, that's separate from the bias circuit. The computer will watch that leg of the circuit even on cars without a bias. So I don't want you thinking that's part of the bias line. It's ground side switched. The driver's off, so this guy has no path to ground. We have a diode here that I drew in the picture. Let's call this 2.9 volts because that's what we saw as the source. It comes through a resistor. It makes its way this way. Can't go anywhere here. That's just my voltmeter. There's no current carrying capability there, so no voltage drop, no current flow there. Tries to go this way. Can it go past the driver to ground? It cannot. So it continues on its way out. I measure the control wire. I'm reading 2.9 volts on the control wire all the way out at the solenoid. And then because the fuse is blown, this is the unique part, because the fuse is blown, that now extends through the coil, comes out the other side as 2.9 volts, comes all the way up to the fuse as 2.9 volts, and then on that part of the fuse is 12. If I would have shown that with the multimeter, do I show that with the multimeter? You dumbass. That needs to be added here too, Caleb. I need another picture here where I'm showing that measurement. I think I showed it in the video to prove it. All the way up to the fuse, I was reading 2.9 volts on one side and 12 on the other. Where's that 2.9 coming from? Through the solenoid, through the feed wire, through the solenoid, through the control wire, back to the computer. It's a bias voltage is what you're looking at. I know this is difficult, so let's add a little more. If the fuse is good, where is that bias? It's still 2.9 volts over here. We still have a 2.9. It might be 5 volts. I don't know. It could be 5, and that's a super high ohm resistor, and my multimeter is causing the drop down to 2.9 volts. It could be 12 volts, as the source, and that's like a 500,000 ohm resistor. The reason I'm reading 2.9 is my voltmeter's dropping it. So you guys understand, I don't know what the source is. I don't care. It is a bias of some kind that is there. Let's call it 2.9 because that's what we saw. If the fuse is good, what do we have? 12 volts here, and that 12 volts, driver's off. That's important, no ground. That voltage runs through the coil. It's looking for a ground. There isn't one. We have 12 volts on this side. Continues on. Is the sensing circuit a path? It is not. The computer's reading 12 volts on the sensing circuit. That's why it's there. It's used for diagnostic purposes. You can look at outputs on the scan tool and know if they're commanded on or off, or if there's opens or shorts. That's where that's coming from. And then it goes this way. It tries to flood this resistor. What is that guy? It's a diode. Guess what? Can't go that way. I'm not going to hurt anything else. So if it's 2.9 on the other side, that answers our question as to why wouldn't the 12 volts overcome the 2.9 and cook something that direction. We'll just put a diode there. Or it could be what I said. Maybe there's no diode. I don't know. I just drew it this way. Maybe there's no diode, and this is 12 volts. And this is a 500 k ohm resistor. And why am I seeing 2.9? Because my voltmeter dropped it. If that was the case, and there is no diode, I have 12 volts coming this way, and I have 12 volts coming this way, am I going to hurt the computer? No. We'll keep the diode in there. So diode blocks it. This comes over this way. So I have 12 volts sitting here right now. This is a working circuit. This is what it should do. This is what we see. Normal off voltage readings, 12 and 12. Do I know anything about this right now? I don't see it. It's not there. This looks like a normal ground side switch circuit that I've seen on a million cars. Unplug the coil, unplug this component. This side stays at 12. What's this side do? Changes to 2.9. How's my control wire from the computer all the way out to, where is this component? Like, I'm only showing this little tiny itty bitty control. Here's my control wire. That is not reality, is it? On this car, the engine computer's under the hood. Where is this evap vent solenoid? All the way in the back of the car. What does that test tell me about my circuit integrity? Let's apply this differently. What's that tell me about the wiring from the solenoid all the way to the computer? It's not opened or shorted. Do you see how nice that is in a circuit analysis test to make sure that your wiring is good? Will that bias voltage of 2.9 confirm to me that that circuit can handle current flow? It doesn't. So it's just an initial test. If I want to check to see if that circuit can handle current, then maybe in my scenario up here when I saw this 2.9 volts and I realized that yeah, my voltage is a little low, so maybe we could argue my ground wasn't quite as good as I thought it was. But once I know which one my control wire is, I would just simply unplug this. I would take my test light to battery positive, because what type of driver is this? It's ground side switched. And then I'd take the scan tool and I'd command that driver to turn on, and I'd make sure my light lights. So in a car with no bias voltage, because there's many that don't have it, do you guys understand that's how I do circuit integrity testing right there? I'd use my test light as my guide. We can also use a working circuit and look for voltage drops and current flow. We'll talk about that in the next one. Yes, sir?
You had 2.9 on both sides. Where was the short to ground at?
Okay, yeah. Well, I'm not really, good question.
Below the fuse.
Yeah, I'm not really covering that in here in this example,
Okay.
but my short to ground was in this part of the harness.
Okay, my problem is why were you reading 2.9 on the other side of the bias voltage if it was shorted?
It wasn't shorted to ground when I did my measurements. It was an intermittent short to ground.
Okay.
And that's where the video, the great questions.
Okay.
You guys, maybe those are great questions, because if that wire that I just circled is shorted to ground, Ed is right. It would have pulled the bias voltage all the way to ground throughout the whole circuit. If that wire was touching ground, Ed, when I did my measurements, we would have read 0 here, 0 here. We would have had 0 at the computer, because this would be the resistor that all of the voltage would drop across on its way to that short. Actually, I take that back. It wouldn't be all of it, because we have an isolation circuit here.
Right.
It would be 0 on this side. You might have read like 0.1 on that side. Just because, you guys follow that? You got a resistor. If this is my source, we're going across one resistor, and then across another resistor before we get to our short to ground. So what do we have? We have a voltage divider circuit again. Voltage measurement between two resistors. It's not going to be 0, 0. It would be some number that would be low. That's just a side note. That's probably too much for you guys right now. But great question, Ed. The answer is when we plugged the fuse back in, we couldn't get it to blow. And so most of our time on this process, on this car, was in locating where that short to ground was. And this was part of the lesson, and I pulled it out because I really was fascinated by seeing high voltage on one side of a fuse. I have another case study I want to refer you guys to. It's on the Premium channel, and your key word is just type in 29 volts. Just type in 29 volts. I had a fuse. I had an engine computer. Ed, you're gonna like be blown away by this too. I've never seen anything like this. I had a fuse that was blown. One side of the fuse read 12 volts, and the other side of it read 29 volts. Not 2.9 volts, 29 volts. It was not a bias voltage. I put my test light on that, and it was I thought my bulb was gonna burn out. This was a legit 29 volts with a blown fuse. What it was this is my ECM, and this was a main power feed to the ECM. It was on a Ford. The fuse was blown, and this side read 12, and this side read 29. I had no comm with the ECM, and it had another power feed that was good that came in. The ECM was also the TCM, and the TCM had a solenoid, the pressure control solenoid for the transmission. When you turn the key on, the computer with this power feed was half alive. So this half of the computer is alive, and this half is dead, and it ended up pulsing incorrectly that solenoid. In the back, the counter EMF of the collapsing magnetic field of an inoperating partially caused voltage to rise and backfed the computer from these spikes. So I don't know if you guys covered it to this level yet, but when you look at, so watch, I'll just show you real quick. Fuel injector, solenoid, relay coil, whatever it is, I'm measuring right here. What does this look like? If I looked at a scope waveform, circuit off, we already covered this. It's 12 and 12, right? So start my line right here, it's 12 volts. What happens when this switch closes? Voltage goes to ground. So you'll see this, right? Looking at a scope waveform. How long this switch stays closed would be how long our pulse width is. Fuel injector maybe, right? Now open the switch back up. This comes back to 12, but it doesn't. It comes up to, typically, fuel injector, you might see 100 volts. You might see a 100 volt spike. Why did that do that? Well, when we had current flow, which is in this low portion, what was this coil doing? What is that? It's a magnetic field. It's a magnetic field. So what happens when we open the switch? What happens to that magnetic field? It collapses. It's a voltage spike. That's the collapse of a magnetic field. Then from that point, it now returns back to 12 volts. That's what it would look like if you looked at a solenoid, a relay coil, a fuel injector, anything that makes a magnetic field. When you turn it on, turn it off, that's what you're going to see. So if I'm taking a transmission solenoid and I'm pulsing it on and off like 100 times per second, how many of these spikes am I making? A whole bunch. I got a computer board that's missing a power feed, so we can backfeed and do things weird, internal circuitry in the computer that is not possible if that power feed was there. And that guy fills this board with pressure, and it was coming out as 29 volts. And when I put it on a lab scope, it was not a steady 29 volts. It had some major oscillations to it. 29 freaking volts. You know what was wrong with that? Fuse was blown. That's it. Plug the fuse in, vroom. That car got an engine computer, that car got a wiring harness, that car got thousands of dollars of components. It wasn't blown. I'm sorry, it was a fuse that was relocated in the wrong spot. So it was an empty fuse. So these numbers are right, 12 and 29, but there was a missing fuse there. The engine fuse was put in the wrong location below it. And the problem started when they put a crank sensor on it and a crank pulley. And on that case study, the crank pulley was incorrect. It was an aftermarket part. It was the right part, but it was just slightly off. It wasn't pushed in as far. And the sync notch for the crank sensor, so you got a crank trigger wheel with all these notches, right? Well, you got one notch that's unique. Let's just draw it as the circle. That unique notch was not being recorded properly because it wasn't the right fit. And so the car never started when they put that in. And so then they created that problem. Wiring harness, engine computer, control module, transmission. They put an entire wiring harness in the car because whoever was troubleshooting that, when they were doing their troubleshooting, they relocated the engine fuse to the wrong location. That's a good one. That's on the premium channel. That one's worth watching. You should watch that video because I addressed the crank sensor fault at the end. I addressed that fuse. Here's my point with all of that. Here's the tie-in. If you're measuring a fuse and you see 12 volts and then some other random voltage that you know the fuse is blown, you're like, that shouldn't be there, right? We know fuses are blown, 12 and 0, that fuse is blown. Test light, 12 and 0. Or light and no light. Any other voltage you see is either A, a bias voltage, which I just explained to you, or B is some kind of crazy backfeed like I'm seeing right here. So if you put your test light on that fuse, what it looked like was bright test light and super bright test light. It was really weird. Never seen anything like it.
When you put your meter on, was the meter pulsing, like
yes.
fluctuating? It wasn't a constant fluctuating.
It was constant 29 average when I put my multimeter on it. I did not see those pulses until I put it on a graphing meter and I saw hash in that signal. It wasn't full up down 29 volts, but there were oscillations in it. Yep.
On and on.
Yep. And when I put my test light on it, initially it was very bright and I had 29 volts and then I remeasured and it was like 18 volts after that. And then it would slowly build back up and it was 19 and 25 and 20. It was crazy. And it was coming from the magnetic and inductive spikes of that transmission control solenoid turning on and off. That's the only explanation I can have. And then I took that same, just to experiment, I took that same Ford system and somebody drove a Ford Ranger that was 2 years newer and I just wanted to see if I would unplug that ECM fuse if I'd have that same condition, and sure enough I did. It was like I had battery voltage and battery voltage. When I unplugged it, I had battery voltage and like 16 or 17 volts on the other side of the fuse with it disconnected on another Ford, just to prove my concept on where it was coming from. It wouldn't run. Key on, engine off, the car wouldn't run. With that blown main ECM fuse, I had no comm to the ECM, the car would not run. Truck would not run. Weirdest thing I've ever seen. Coolest case study ever. We caught it all too. It was here. We did it right here with the class. It was freaking awesome. Watch that one when you get a chance.
Look at the scan data for the transmission control module. Or
I couldn't talk to it. The ECM, ECM and TCM were one unit on that model.
Couldn't communicate.
Couldn't communicate. No communication, no start, no spark, no injection pulse, no fuel pump operation. No communication. Start doing my power and ground checks, and that's when I saw 29 volts on 2 of the power feeds, because this was split. This was split. 2 of the power feeds, as I'm doing power and ground checks, I got 29 volts on. And so I went around in circles trying to find out where that 29 volts was coming from before we found it. Because I might have had a student check the fuse and it was lit on both sides and maybe didn't pay attention. I don't remember exactly the whole process, but really, really cool case study. That's one of those ones you say always and never. A blown fuse, you're always gonna see 12 and 0. Nope. Could be a bias voltage there. What do we see on our Cobalt? 2.9 volts on the other side of the blown fuse. I've seen this in other times. I see 6 volts on the other side of a blown fuse. I'm like, bias voltage. That's my first thought. This one's weird. Don't think about that as the norm. Bias voltage is your next thought. That is an output circuit. That's bias voltage. I'm going to skip this one for now. I'm going to do this VW. This is the one I worked on this morning. This part that I'm skipping here, the highlights of this one, it's an oxygen sensor circuit that it's a ground side switch circuit. What I labeled this as is bias voltage that lights a test light, and I always said forever, bias voltage is never going to light a test light. It's such weak voltage. It comes across a very high ohm resistor. Ultimately, what we found at the end of this circuit, or at the end of this case study, you guys can watch this. This is on the premium channel under chapter 3, bias voltage lessons. I have this exact case study recorded if you want to see it. But at the end, what we found, last statement, GM forever has been, all manufacturers have been resistant, and I have noticed that as well, that they're starting to have their techs use test lights. I mean, I'm like, has GM been watching me for the past 10 years? Because I'm shocked to see this, and that was honestly where I started when I taught you guys yesterday the test light on the 5-volt reference circuit. You know where I learned that from first? GM. I was like, I can't believe GM is telling me to load this 5-volt reference circuit with a test light. I was like, hey, that's awesome. I'm gonna start doing that. And so I was shocked, but I agree with you. Some manufacturers are finally coming along to the fact that resistance measurements are getting people in trouble. And that's awesome to hear. So if the camera didn't pick that up, GM is starting to write their charts with a lack of this type of testing, but this is still widely what it's been for the past 50 years. These resistance measurements, and it's crap, and they're not giving us this kind of information. And it's a shame. It really is a shame. Guys, I appreciate your attention. Thanks for letting me join you guys, and good luck in your career path. And if you need any help, I told you guys to jump on the premium channel. I'll give you guys access as students of Rosedale. We can interact from there too, watch a video. My suggestion is you do it and watch one video a day. Watch one a day. My average video length is 40 minutes. Spend 40 minutes of your day, 5 days a week. It'll really, really help you. It's foundational. It applies across the board from a 1982 first year engine computer system all the way up to 2000. That's kind of what I focused on when I wrote this. I wanted it to be something that could carry through the test of time, something that applies universally to everything. So appreciate your time, guys. Hope to talk to you on the other side on the internet.